In the previous week, we talked about RE model for common emitter. Today, let's start to talk about RE model for common base. And if I return back here, yeah, this is for common emitter it was. And this is the RE model for common emitter. I want to take photo for this because we have a comparison. Okay, copy. Now let's go to the common base and see what the difference between common base and common emitter. This is, by the way, this is the common base basically. And I will change here this. Where's the pin? This pin. Yes, I will change. Just a minute. I will change this with this diode. And here the basic IDC, excuse me, this one. Let's expand. Yeah, here. For common base, if we return back to the figure of this configuration, see here, I have this in, IE in, IB out, and IC out. But see this, IO usually and ZO inside. Here, IC is opposite, outside. So this is here. This is out. So this is in. This is first. Second thing. Usually we know that means so this is out, so it's here like this. IC in common base, it's alpha IE, and this is alpha IE. And here we are using small because here we are dealing with AC current. So see here, IC alpha IE. In the previous model, if you remember, I will return back and I will compare now. Here this. Go up, 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 up. Here. Yeah, this is for here. And this model, see this is the basic, same thing. I have this one. It is IE out, IC in, and IB in. So here, if you remember, IO and IC will be on the same direction. So in common emitter, IO equal IC, same direction, and IC equal beta IB. In common base, it's opposite. It's opposite, it's very important. See, this is same. IO same I, C. IO same I, C. Now this one. Here, as you see here, IO is opposite to IC. Why is this? I will tell you, just a minute, give me a chance. Now we have this diode. We didn't solve this diode. In common emitter, it was, let's go up, sorry, here. It was your common emitter like this, beta RE. We solve it like this, and we found it's beta RE. Now let's see about common base. In common base, just we don't have anything else. This diode is usually we find or we use dynamic resistance. So here it is RE, only RE without beta. So this is the model. Let's copy and let's compare on the paint together. Okay. See this? See this? This is common base, common emitter. In common emitter, this is input, and this is input. This is output, and this is output. So from input, see IB like IE. Here we have beta RE. Here we have just RE. This is the first. Second thing, here, see, IC like IO. Here, IC out, IO in. Okay, good. Here we have RO. Here we have same RO. No problem for this one. Now let's see dependent current source. This one is beta IB down. So small letter is correct. Small curse. Here we have to use IC up equal alpha IE. So based on common base and common emitter, you can use this one or this one, as I explained here. And excuse me, when we finish, take photo for this, or write by your hand, or you can take from screen and keep this in your mind because it's very important to use later. Okay, yes. Now, else. How we can solve this one, what is the benefit for this one? Now, let's go to the common base and start to solve common base. See, for common emitter, if you see here, we have like this. If I have input, I have flipped output. Why is this? Returning back to the previous lecture, and here we have, see this. VO is minus. Where is VO? This one, VO. Exactly. Now, let's solve for common emitter, repeat, and return back to the common base. Yes, give me this. Now, I have V out, so let's withdraw the V out, and it's beta IB. So this RC with RB on parallel. So I can write V out equal, I use Kirchhoff, equal minus beta IB multiply RO RC in parallel, and we found IB value, so we can, I need this, You can continue with this. I need this. Here we have minus. Because VO here, if I continue the complete the Kirchhoff, this is C up and this is down. So that means we have flip in the phase between input and output. Continue, you can find IB later about this one. Find V input, VIB or VB over RE, then you can find the value. It's not our job today. See here, then you can find IB, then you can take beta with beta. So we have this value. Now let's go to the common base. Today, okay, which one? Common base. This is the common base. In common base here we have two cases, unbypassed or with bypassed. Unbypassed, that means we don't have any capacitor here. So this RE should enter in our consideration. You see, we don't have any capacitor. This case we don't prefer to use, so I will not. We will not. You are not responsible in exam for this one. What we have to study with bypassed. Bypass, that means this RE will be short circuit. So this unbypassed will be cancelled. Not just a minute. Combase. Yeah, here, correct. Correct. Sorry, excuse me. Yeah. Or with that, here, see the circuit. Here. Here we have RE, VEE, RC, VCC. First of all, short circuit. Okay, so we have short circuit. Now let's calculate. This is input circuit. This is output circuit. So ZI here is directly is RE. If we have this, so RE with RE. ZO just we have RC, and if we have RO, it's RO with RC. This on the question. Okay. Else, I want to calculate the most important thing is AV. AV here is this. CAV. I want to share. I compare with again with common base with common emitter. See here, this is from up to down. Continue here. So V out here is same direction. So it's alpha IE with RC. So here, no flip in phase. So just common emitter flip the phase of volt. And in common base, there is no flip on the volt. See here. RC over RE. Now, I want to calculate AI, amplifier of current. What is this? I want to find IO over IE, IO over IE. How we can find this? Here. IE equal here, IE, IO equal, let's focus on IO. If this is open circuit, so there is no current. So see, IC and IO are opposite. IC equal minus IO. And IC, it is this, alpha IE. So IO, from this graph, you can see IO equal minus IC minus alpha IE. So here we have something very important with me. Common base, flip current, common emitter flip voltage. Repeat. Common base, flip the current. If I want to flip the current, so it's common based. If I want to flip the current, common base. If I want to flip voltage, common emitter. Repeat. If I want to flip current, it is common base. If I want to common voltage, it is common emitter. So I will select my circuit based on what I want. I want to flip the volt, so it's common emitter. No, I don't want to flip the volt. I want the same volt, so common base. I want to flip current, so common base. No, I don't want. I need to use common emitter. So the based on this case, but in all cases we have one flip, either current or voltage based on this formula. See here, it is -1. Phase relation, the fact that AV is positive number shows that VO and R are the same phase for the common. Here you can also add RO as effect for this circuit. Now let's solve this question for the network of figure. This question came many times for 5.8, so take care for this one an example. He asked me to determine, okay, ZI, RI, ROAV. So directly short circuit, and start solving for this one. Calculate IE, then RE, then find others value. So again, start with DC, then go to the AC. Any question? Any question about this? Okay. Collector feedback 5.10. This is cancelled. This is cancelled, so skip it. See the formula? Collector DC feedback configuration also cancelled. And now we start something called effect of RL and RS. What is this? Okay. If we can see this configuration here, see here just we have, okay, I will expand this for you. Yes, now it's good. See, go up. Now, see now these three configurations. Start from A, then B, then C. A, for example, here we have RB and RC, but we don't have any load and any generator. Second one, RB or B, we have a load, but without generator, without effect of generator. This is the common view or general view. I have here RS for generator, and here I have here RL for load. So if I want to write, I will write AV no load, AV with load without RS, AVS, that means I have RS and I have R load in my study. Repeat. Until now, what did we calculate? AV, this is just for no load, without RL. If I add RL, it will be IV load. If I add VS, that means called AVS, that means I enter here load and configuration and load for both load and RS, for one for load, one for generator. Which one is the best? Which one in general? Best one is AV no load. Now you can say this. General case, and this is the common case, is AVS. How we can calculate them? Start from this. AV no load, it's VO over I. AV load, it's VO over I with RL. AVS is VO over VS with RL and RS. Usually, we can consider that the load gain of amplifier is always the no load gain. Usually, if you have, for example, AVS, so I will write this AVS. Usually, if I add R, so I will have decrease in I. So usually, AVS less than AV load less than AV no load. Because here you are adding R to your study. So adding R, that means decreasing. decreasing loads. So IVS is less than IV load, is less than IV no load, and we will solve this in practical example later. So here AV no load is bigger than AV load, AVS. How we start? We calculate this directly. Let's take the circuit. Same as this one, same this, but I will omit transistor I, and after that I will use equivalent circuit. Okay, let's start to say this one. This is now we omit the transistor and we used here this one. This is equivalent circuit for transistor. This configuration is very important. Now I will add RP, and now I'm gonna RS for generator, then RC, this is for configuration, RL for load. Then I will start to calculate AVS, AV, no load, AV load, and AVS. Okay, start step by step. First of all, AV no load. AV no load, you know this AV no load, this AV no load. AV no load is from here to this one. AV no load is minus RC RO over RE. Okay, let's enter this part. Okay, fine. Again, yes, this one. This is called AV no load. Now, I will enter another part, AV load. So this is AV load. I entered IRL. So AV load, it is as you see, minus RC RO RL over RE. Last thing, it is this. Gonna use another this one here. AV is this is from here to here. Yeah, all. How we can calculate? Okay, wait for this one. How we can calculate this one? Okay, let's start. Every load we calculate here directly. Just we add RC RL to this configuration. So it's minus RC RL, and if we have RO, we can add to this configuration. So it's easy. Now, how we will calculate AVS? Now, let's make this circuit as like this one. See air conditioner. I will say this is here to here. This is using this one called ZI, for example. So we can write A for this one, or let's use this one. ZI, by the way. So VS or VZI equal ZI over ZI positive RS voltage divider. For example, it is it multiply VS. It's multiply. So VZI, this is called V load. So V load equal ZI over ZI positive RS dot VS. Okay, let's see our book, and if there is any mistake, we will correct together. Let's check. I don't know. Okay, VI is ZI VS over ZI RS. VI, I said here VZI. If I take VI over VS, VI here over VS, what will happen for me? Here we have stick. See this? It is ZI over ZI multiply or positive RS. Good. See here the trick that we used in our book. I said VI over VS. I can rewrite as, see my hand, VI over or VO. Okay, sorry. So if I want to write AVS, it is VO over VS. So I will write as two steps, VO over VI, then multiply VI over VS. So again, return back to the configuration. I have this circuit. I have here load RL, and I have here RS generator. And here. So here I divide to two parts. This is VO. I need VO over VS. I will use this step, VO over VI, then VI over VS. So this over this, multiply this over this. If you want to calculate, you will omit this with this, then you can get VO over VS. That's the idea? So AVS here, I explained before, it's ZI over ZI plus RS multiply AV load. And I explained before, if you remember this one. So AVS, it's ZI, you have to calculate ZI over ZI plus RS multiply AV load. Any question for this until now? It's clear? Any question? Okay, now let's solve this example using the parameter value for fixed bias configuration. Example 5.1. So here you have to return to this example 5.1 and find the value. What are the value? First of all, you have to calculate IE, RE, then you find ZI, ZO for this one. So let's now start some joking morning. I brought this question before. So one student answered me like this based on the configuration. Which configuration? Which solution? You have to solve by your hand, then prove this one. So maybe I can bring the same question. So you have to start with 5.1, then go to those. So equation, excuse me, I have to calculate AVL. So it's minus RCRL over RE. Then I have to calculate AVS. See here, it's 133, here 170. It was there, for example, with load, without load, that's 280. So first of all, we have to calculate AV no load, then AV load, then AVS. So in exam, excuse me, you have to start with this example, 5.1, find all the parameters, then go to the rest of this, for example, AV load, AVS. I want to now to know if I connect any load, RL or Z maybe be a real number or complex, that means sure AV will decrease. If I have not optimal generator, and this is practical case, so also sure AV will decrease. So AV load, that means I have optimal battery or optimal generation, and we don't have this in our life. Second one, if I connect to the load, and this will different from node to another. For example, here I have 4.7 kilo ohm. It's maybe, for example, change to be 200 kilo ohm, 300 kilo ohm, based on the question. So if I increase the load, that's mean AV will decrease. AV will decrease based on this one, sorry, RL. Okay. Now that I did same example before. For voltage divider, it will be exactly like fixed bias configuration, but you will add R Thevenin or R1 parallel with R2, and you can find the values for this one. Okay, now let's continue. And here we have, for example, emitter follower. If we don't have RE, this is cancelled, by the way. Just we are dealing with case if we have here capacitor, or we can say by bypass capacitor. This is a little bit hard, so this one is cancelled. We don't have this one. Now, 5.13 determining the current gain. Current gain. For determining the current gain, why that's AI. Usually we are focused about AV. But if I want to calculate AI, we have the system, for example, I in, Z I in, I out in, Z O in, and we have VO, VI. So how we can find this? Okay, let's see now how we can calculate AI. AI, it's IO over II. IO, it's VO over RL. II, it's VI over ZI. Now let's take the ratio. So here we have it. AI here, as you see, it is minus. As I told you before, every time we have flip, either in current over or in volt. So IL minus AVL ZI over RL, and this is memorization for exam. You have to know this. Okay. Now, here in the same question, he asked me calculate AI, and we found here AI, it's, for example, with load or without load. Here AI, it is 73.2, and see this is positive because here we are using common emitter. So AI here is positive. If I have, for example, 1 microampere, it will be 73.2 microampere. That's mean amplifier in the current. Okay. Now, this is for common base. Here we have just -1. That's mean there is no any amplifier for common base. Just we have amplifier for volt and current on the common emitter. Whereas if I want just to flip the current, just to flip the current, so we are using here common base. That means here AI is -1. Okay. Summary table. We have the summary table as you see here. And what is we are responsible for the summary table? See this one. I need fixed bias. ZI, it's medium, about 1 kilo ohm. ZO medium is 2 kilo ohm. AV is high, see 200. And AI also high, it's better. If you don't, for example, to manage that is a little bit hard. You have to know this. And you can say AI equal AV multiply ZL over RS. This is formula before. Now, this is voltage divider. Also, you are responsible for voltage divider. After that, here we have unbypassed emitter. Yeah, it's cancelled. Just we are dealing with CE because this is a common base. Now emitter follower also cancelled. Emitter bias just if you have RC, so it's returning back to the same cases before. So if just we have what we can see bypass is our response. Otherwise, no, we don't need. So if we have, we can say emitter bias, that's like fixed bias configuration. I'm here in our book. So this is unbypassed, this is cancelled. Emitter follower is cancelled. Common base, yes, in exam. And see here, medium, AV it's high 200, whereas there's just one, that means just change the direction of current in common base. Collector feedback also cancelled. Here we are talking about the second part, how we can configuration for AV load. If we are, for example, common base, common emitter, so excuse me for this, and you can find AV load, ZI, ZO, including RO. If you have RO, just it's RL, RC, and RO. Here for voltage divider, same thing, just we add R1 and R2 on parallel. This one is cancelled. And this was, yes, I'm responsible for this one to calculate common base 4. So we have now common base, fixed bias configuration, cell bias configuration, and voltage divider configuration with CE, with bypass capacitor. Okay. Continue in our book. This is how we cancelled this one. We don't need this one. If we don't have RC, this is cancelled. This is cancelled. I will write here on the screen. This is also cancelled. And this is also cancelled. This is also cancelled. And here we will talk about something in general. For this is inshallah for next week, about something here they skipped called before this. Yeah, not before summary. Yeah, called two-port system approach. Until now, we studied the equivalent model for BGT, and we found that's been called RE, and we got Y. Next week, we'll start another model called hybrid model. This is the hybrid model. This is the hybrid model, and how we can shift from or move from RE model to hybrid model. So hybrid model is another model that we can use in our study. And if you open any catalog or any data sheet for transistor, you can find something, not RE, H. What is this H? This is called hybrid model. Hybrid model based on many models. We have volt model, we have I model, or we have Z model, we have Y model, we have hybrid model, we have S model. So this is I guess you studied or you'll study in circuit theory called port or four-port models. Four-port models. So if I open, for example, for you, internet, you can find four-port models in circuit theory. See, you can find here four-port genesis model. Okay, if I open, for example, this one, you can take this one. This is four-port or port model. Here we have one port, two port, And here we have 4 port. I have to show you. Here they are using 2 port, but I prefer to use, yeah. Or sometimes I say 4 port. In 4 port, maybe you can find better than this one. And we start to go to direct to something called hyperport. I will study this one in details. Okay. By the way, I guess this one should continue this week. No, in this one next week we'll continue with this one and study about the sport, how we can deal with the circuit as a configuration or as a block. Then we'll go to the hybrid model later, Darlington and others later next week. So we have a lot of things in this chapter. Excuse me. That's for today. Any question? I hope to be not hard, not easy. But we'll continue with this one. We have a lot of things. Cyber mode, I'm going to talk about this one. But next week, we'll just start from this one about multi-stage and hybrid model for this configuration. Yeah. This is for today. Any question? Easy or hard? It's easy or hard? Little bit hard.